Hello everyone, in this video we're going to explain Taylor and Maclaurin series and how we use them to approximate functions. This is based on section 11.10 and 11.1. Let's start with the big question. Why do we need to learn Taylor and Maclaurin series? The reason is that there are many integrals that cannot be solved using the techniques we've learned so far. For example, the Gaussian integral, which is fundamental in statistics and forms the basis of the normal distribution, cannot be solved directly. However, we can break down such functions into a polynomial using a Taylor or Maclaurin series, and then the integration becomes solvable. So what is a Taylor series? A Taylor series is an infinite sum of polynomial terms that approximates a function near a specific point. For a function of f of x, the Taylor series centered at a point A is f of x equals f of a plus f prime of a times parenthesis of x minus a, and so on. An integral, this is f of x equals the sum from n equals 0 to infinity of f to the nth derivative at a divided by n factorial times parenthesis of x minus a to the n. As you add more terms, the polynomial curve gets closer to the original function f of x. So where do these terms come from? First, let's recall the geometric series. The sum from n equals 0 to infinity of r to the n equals 1 plus r squared plus r cubed and so on, which equals 1 over parenthesis of 1 minus r, where the absolute value of r is less than 1. Now let's substitute r with x. Then we get 1 over parenthesis of 1 minus x equals 1 plus x squared plus x cubed and so on, which is the same as the sum from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. Now let's substitute r with x. Then we get 1 over parenthesis of 1 minus x equals 1 plus x squared plus x cubed and so on, which is the same as the sum from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. Now let's compare how well certain polynomial functions approximate the original function f of x, which equals 1 over parenthesis 1 minus x. Let's define three functions: g of x, h of x, and f of x. We say that h of x is a better approximation of f of x than g of x because the first and second derivatives of h match the first and second derivatives of f of x equals 0. On the other hand, g of x only matches the first derivative of f at 0. To see them more clearly, here's their values and derivatives are at 0. So overall, h of x is a better approximation of f of x than g of x because it more closely matches the behavior of f at x equals 0. How about other functions that are not 1 over parenthesis of 1 minus x? We can write any continuous function in this form. f of x equals c naught plus c1 times parenthesis of x minus a plus c2 times parenthesis of x minus a and so on. Now, consider evaluating this function and its derivative at x equals a. When we plug in x equals a into f of x, all the terms with x minus a disappear except the first one. So f of a equals c naught. Next, we take the derivative of f. When we plug in x equals a again, all terms with x minus a vanish except the constant left over, so f prime of a equals c1. For the second derivative, only the term with x minus a squared contributes and the coefficient simplifies so that f double prime of a divided by 2 equals c2. For the third derivative, a similar pattern appears, and we find that f triple prime of a divided by 3 times 2 equals c3. The pattern can be generalized as c sub n equals the nth derivative of f at a divided by n factorial. It is important to note that the infinite sum can substitute the original equation only when the absolute value of the ratio between the terms is smaller than 1 or else the sum diverges. What is the ratio between the terms here? Well, it's tempting to think it's just x minus a, so that the absolute value of x minus a is less than 1, but that's not always the case. More generally, the ratio is the absolute value of a sub n plus 1 divided by a sub n, because the ratio between two terms doesn't necessarily equal x minus a. For example, imagine a function where the nth derivative at a equals 0 when n is an even number. That breaks the simple x minus a pattern. So to find out for what x values the series converges, we use the ratio test. Here's how it works. If the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, then the series converges in that range of x. The positive boundary of this range is called the radius of convergence, which we call capital R. If the limit is greater than 1, the series diverges, so the values of x in that region won't work. And if the limit equals 1, then the test is inconclusive, meaning we can't determine convergence from this test alone. Putting this all together, the interval where the series converges is from a minus r to a plus r. That's the interval of convergence, but you can have to test the endpoints separately to see whether they converge or diverge. Therefore, the Taylor series of a continuous function f of x at x equals a is this that we saw in the previous slide. This is called the Taylor series of f at a, also known as the nth degree Taylor polynomial of f at a, written capital T sub n. The value a represents the point around which the function is being simulated, and we call this the center of expansion. Now here's an important note. From the definition, we can see that f of x needs to have derivative of all orders. In other words, it must be smooth at the point A. And the Taylor series of at the point A is unique. That means there's only one correct Taylor series expansion around that point. Let's look at an example. Finding the Taylor series for cosine x centered at x equals pi over 2. Feel free to pause the video and solve it by yourself first. Okay, now to start, we compute several derivatives of cosine x and evaluate them at pi over 2. We notice a pattern. The values alternate between 0, positive 1, and negative 1 depending on which derivative we're taking. Using those values, we plug them into the Taylor series formula. Since some derivatives at pi over 2 are 0, a lot of the terms drop out, and we're left with only the odd-powered terms. So the first few non-zero terms of the series look like this. Negative 1 times x minus pi over 2 plus 1 over 3 factorial times x minus pi over 2 cubed, and so on. This alternating patterns continues forever, and we can write it more compactly using sigma notation. The sum from n equals 0 to infinity of negative 1 to the n plus 1 times x minus pi over 2 to the power of 2n plus 1 divided by the parenthesis of 2n plus 1 factorial. This is the Taylor series for cosine x centered at pi over 2. Here's another example. Let's find the Taylor series for e to the x centered at x equals 2. We start by noticing that the derivative of e to the x is always e to the x, no matter how many times we differentiate it. So every derivative of e to the x at x equals 2 is just e squared. Now we plug that into the Taylor series formula. That gives us the sum from n equals 0 to infinity of e squared over n factorial times open parenthesis x minus 2 close parenthesis to the n. This is Taylor series written in sigma notation. If we expand it out, it looks like this. What is the difference between a Taylor series and a Maclaurin series? A Maclaurin series is just a Taylor series centered at 0. Let's find the Maclaurin series for e to the x and figure it out, its radius of convergence. We start by noting that all derivatives of e to the x are just e to the x. And since e to the 0 equals 1, that means every derivative at 0 is also just 1. Using the Maclaurin series formula, we plug in those values. So f of x equals the sum from n equals 0 to infinity of 1 over n factorial times x to the n. That simplifies to the sum from n equals 0 to infinity of x to the n over n factorial. And if we write out the first few terms of the series, we get this. Now, let's find the radius of convergence of the Maclaurin series using the ratio test. We take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. That becomes the absolute value of x to the n plus 1 over open parenthesis n plus 1 close parenthesis factorial times n factorial over x to the n. Simplifying that, we get the absolute value of x over n plus 1. Now as n approaches infinity, this expression approaches 0, and 0 is definitely less than 1, no matter what x is. That means the series converges for all values of x, so the radius of convergence is infinite, and the interval of convergence is from negative infinity to positive infinity. So can we always replace a function with its Taylor or Maclaurin series if it is smooth at the point? The answer is no. Imagine a function that is flat at the origin, meaning all its derivatives at x equals 0 are 0. But the function is not identically 0, so the Taylor series doesn't match the original function at all. It completely flattens it to the x-axis and doesn't simulate the function. This example shows that being smooth isn't enough. We need something more for a Taylor or Maclaurin series to actually represent the function. So what is the criteria for a function having an interchangeable Taylor series, meaning a series that actually equals the function? The key condition is this. If the limit as n goes to infinity of nth degree Taylor polynomial, capital T sub n of x equals f of x, then the Taylor series represents the function. In other words, the Taylor series only truly works when the polynomial gets closer and closer to the function itself as we take more terms. We can express the function like this. F of x equals T sub n of x plus R sub n of x. T sub n of x is the nth degree Taylor polynomial, and R sub n is the remainder, which is the area between the function and the polynomial approximation. In full, the function can be written as the sum from n equals 0 to infinity of the nth derivative of f at 0 over n factorial times x minus a to the n plus the remainder r sub n of x. The remainder itself is given by this formula. R sub n of x equals the integral from a to x of the n plus 1th derivative of x evaluated at t over n factorial times open parenthesis x minus t close parenthesis to the power of n with respect to t. This expression comes from repeatedly converting differences into integrals using the fundamental theorem of calculus and apply integration by parts to cancel out terms. So this remainder tells us how far off our Taylor polynomial is, and the smaller it gets, the better our polynomial simulates the real function. R sub n of x, the remainder, can be really hard to calculate directly, but there is a shortcut we can use to estimate it. If we can find an upper bound m for the n plus 1th derivative of f, then we can say that the absolute value of r sub n of x is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the power of n plus 1 for all x values within a certain distance d from a. In other words, if we can find a maximum value for the next derivative, we can plug it into this inequality and get a bound on the error. This is called Taylor's inequality. So if the limit as n approaches infinity of t sub n of x, which is the Taylor polynomial, equals f of x minus r sub n of x, and if the remainder r sub n of x goes to 0, then we know the Taylor series does converge to the function. That gives us this conclusion. The limit of t sub n of x as n approaches infinity equals f of x. We want to prove that e to the x equals the sum of its Maclaurin series. We start with the function f of x equals e to the x. All derivatives of this function are just e to the x, so the n plus 1th derivative is also e to the x. Now suppose the absolute value of x is less than or equal to some constant d. Then the maximum value of e to the x on that interval is e to the d. That gives us on upper bound m equals e to the d. So by Taylor inequality, the absolute value of the remainder r sub n of x is less than or equal to e to the d over n plus 1 factorial times the absolute value of x to the power of n plus 1. Now we want to take the limit of that bound as n approaches infinity. We look at the limit of e to the d times the absolute value of x to the n plus 1 divided by n plus 1 factorial. As n grows, factorial grows faster than any power, so this limit goes to the 0, no matter what x is. This means r sub n of x is squeezed between negative and positive version of that bound, and both of those limits goes to 0. So by the squeeze theorem, the limit of r sub n of x as n approaches infinity equals 0. Since the remainder goes to 0, we conclude that the limit of t sub n of x, the Taylor polynomial, equals f of x. And since this holds for every x, we now know that e to the x equals the sum from n equals 0 to infinity of n's derivative of x as 0 over n factorial times x to the n. But since every derivative of e to the x at 0 is just 1, we get the familiar series, the sum from n equals 0 to infinity of x to the n over n factorial. And one final note, the fact that remainder r sub n goes to 0 is actually stronger than just knowing the radius of convergence is infinite. So we don't even need to use the ratio test here. Now let's go back to the question we asked at the beginning. Finally, so how do we solve the integral of e to the negative x squared? Well, now we can make use of the Taylor series result we already found for e to the x. We know that e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. If we substitute x with negative x squared, we get e to the negative x squared equals the sum from n equals 0 to infinity of negative x squared to the power n over n factorial. That simplifies to the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over n factorial. Now we want to integrate e to the negative x squared. We do that by integrating by the whole Taylor series term by term. The integral of e to the negative x squared becomes the integral of the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over n factorial with respect to x. That gives us the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by n factorial times 2n plus 1 plus a constant of integration c. And just like that, we've solved an otherwise impossible looking integral by turning it into a series and integrating term by term. This shows how powerful Taylor series are. We can even use them to generate new series by substitution and integration. Here's our team members, and thank you for watching a long video.